then you can infer who is the center of attraction of that crowd. This is exactly what astronomers also did. Okay, so what they did is they measured the distances to a kind of star clusters called globular clusters, and they found out how far away they are, and then they found out how they are distributed within our galaxy. So to know more about this, we have to go back to the year 1914. So in this picture, this is a very famous astronomer who lived during the early part of the 20th century. His name is Harlow Safely, and he was the head of the Harvard College Observatory. Safely, back in 1914, started to study large groups of stars called globular clusters. So here is a picture of a globular cluster. It's a star cluster. There are anywhere from 10,000 to million stars which are present within a region that's roughly about 300 light years across. Okay. In astronomy, we use a unit called parsec. Okay, some of you who have read astronomy would know 1 parsec is roughly about 4 light years, 3.26 light years. So in terms of parsec, globular clusters are typically anywhere from 20 to 100 parsec across. That's roughly about 300 light years. And within that region, there are anywhere from 10,000 to millions of stars present. So safely using the 60-inch reflecting telescope, which was one of the largest telescope back in the early 1900s, using that, he carefully measured the positions of globular clusters in our galaxy, and he plotted their positions. Okay, so what we are looking at here is a graph. So I'll take you through this graph. The horizontal axis is distance from us in terms of kiloparsec. Okay, that's what KPC means, kiloparsec. Those are 1000 parsec. And remember that 1 parsec is roughly 3 to 4 light years, 3.26 light years to be exact. So this red dot is us. That is the solar system, and every black dot that you see here is the position of a star cluster, globular star cluster, that's safely measured. This horizontal line is the disk of our galaxy. So he was measuring the disk, how far away these globular clusters are from us, and he found out that these globular clusters are not centered around us. They are not centered around the solar system, which means that we are not at the center of our galaxy. But in fact, he found out that these globular clusters seem to be centered around a point that's anywhere from 15 to 20 kiloparsec from us. So that means that our galaxy seems to have a morphological center, and we are not at the center. So then subsequently, other astronomers also started replicating these observations, and with better distance estimation. Safely had huge uncertainties in his distance estimations. So with subsequent distance estimations, the distances to these globular clusters became better known. And so here is a more revised 1990 galaxy, and you can see that they are all centered around a point that's roughly 8 kiloparsec from us. So that is 8,000 parsec. In terms of light years, that roughly translates to 27,000 light years from us. So that means that our galaxy does seem to have a morphological center, and we are not at the center. The center is roughly 27,000 light years or 8 kiloparsec from us. So since then, okay, astronomers have been measuring the distance to the galactic center based on mapping the distribution of star clusters. And so these are various team measurements, 1975 measurements, 1980, 1985, 86, 87, 91, etc. And you can see that almost everybody get more or less the same value, okay, roughly somewhere between 7 to 8 or sometimes more than 8 kiloparsec. And these are the measurements from the teams that won the Nobel Prize. Okay, so Andrea Ghez had published a paper back in 2008 where they showed that the distance to the center of our galaxy from us is about 8.4 kiloparsec. And this is the work by Reinhard Genzel's group, and their value also matches. So now there is a consensus among astronomers that our galaxy has a center. We are not at the center, but in fact we are displaced by the center by about 8,000 parsec. So what is interesting here is that these set of observations were started by Harlow Safely, whose photograph I showed earlier, and that his work started in 1914, and he more or less completed his analysis and came up with the result that our galaxy had a center by the year 1990. So historically, if you look at it, 1914 was when the First World War started, and 1918 was when the First World War ended. So while the rest of the world was fighting and going through a lot of turmoil and agony, Harlow safely was quietly working from the Harvard College Observatory. And by the time the World War got over, safely had come up with this result that what the architecture of our galaxy is. Okay. So I just skipped this slide. This is just going a bit into detail. So currently, what we have a fairly good understanding of how our galaxy looks like. So if you were to look at our galaxy from above, our galaxy looks like a spiral structure, has a spiral structure with a planar geometry, with a disc-like geometry. So this is the same view of our galaxy, how our galaxy would look if we could look at it from outside. We are seeing it face on here, and we are seeing the same galaxy edge on here. So it's like a disk, and this is the center of the galaxy, and the solar system is about 2/3 the distance from the center. Okay, so the entire diameter of our galaxy is roughly 100,000 light years, and we are about 23,000 light years from the center of our galaxy. So this is the architecture or the anatomy of the Milky Way. And so if we are not at the center, going back to the original question, then what is at the center? Okay, so what is at the galactic center? So this, now we are getting into the topic of the 2020 Nobel Prize in Physics. Now, some of you may be interested in stargazing. Okay, so I don't know how many of you are doing stargazing, but if you are doing stargazing during the months of July, August, September, or October, you can find the zodiacal constellation Sagittarius. Okay, this is Sagittarius over here. Okay, this entire region, and for example, this month October, you can see Sagittarius in the southwestern part of the sky. The constellation will set in the southwestern horizon by about 10 p.m. or so. So between 8 and 9 p.m. is probably the good time to look at the sky to spot Sagittarius. And the reason why this constellation Sagittarius is important is because if you are looking in the direction of the constellation Sagittarius, then you are looking towards the center of the Milky Way galaxy. So in other words, the galactic center, our galaxy's morphological center, lies in the direction of the constellation Sagittarius. So I'll show you some photographs that students of astronomy club, this amateur astronomy club called Astro Kerala, took of the Sagittarius, the region of the sky where Sagittarius can be seen. So this is a photograph that a student in IIST Trivandrum took, Srirag SG, using a DSLR camera. Okay, you can also do this with do this kind of astrophotography. So what you are looking at is the general region to the constellation Sagittarius, and somewhere behind this dark column that you are seeing is that center of our galaxy. Now the reason why I'm showing this picture is because it tells us something about the difficulty in observing the center of our galaxy. You can see that there are a lot of stars in this picture, but in addition to the stars, there's this dark band of that is running across the photograph. Okay, so this dark band is interstellar gas and dust that belongs to our galaxy. When we are looking towards the galactic center, we encounter this large column, okay, the thick curtain of gas and dust, which obscures our view. So if you are trying to look at the center of the galaxy at visible wavelength regions, the huge column of gas and dust that's present between us and the galactic center will completely scatter all the light. So even if there's a lot of light coming from the galactic center, they get scattered as they pass through this thick curtain of dust and gas. So it blocks our view to the heart of the galaxy. Okay, I'll show you one more astrophotography thing. So this was taken by Fahad Hassis, who graduated from IIST a few years ago and now working in ISRO in Trivandrum. And Kiran Mohan also studied post-graduation in IIST and now he's working in ISRO. So they also took pictures of the direction of the constellation Sagittarius. So this is how the galactic center looks if you do astrophotography. As you can see, you cannot see very much. That's because of this thick cloud of gas and dust. So what astronomers have been trying to do is they have been trying to look outside of the visible wavelength region. Okay, so as you know, the electromagnetic spectrum runs from radio to gamma rays, and so its own visible wavelength, the light is severely extinguished because of dust. But outside of the visible wavelength region, it is possible to look into the galactic center. So what I'm going to do next is I'll show you some wide field images of galactic center taken at infrared, X-ray and radio wavelengths. Okay, so there are telescopes that can collect infrared photons, there are telescopes that can collect X-ray photons, and there are radio dishes that can collect photons emitted at radio wavelengths. So I'll show you those pictures. So here is the first one. This is real image. Okay. This is taken by the Hubble Space Telescope and the Spitzer Space Telescope. Both are space telescopes. Hubble is optimized to look at the universe at visible wavelengths and at infrared. And Spitzer is exclusively a telescope meant to look at the universe at infrared wavelengths. So here is a picture of the galactic center, and you can see that there's a lot of stars, gas columns, etc. present there. In fact, there are some star clusters, etc. Okay, so in infrared, the galactic center looks like a very crowded region. Now, what you are looking at now is a radio image of the central regions of the galaxy. Okay? This is a false color image. What I mean by false color is that our eyes cannot see radio wavelength photons. So what the radio telescopes do is they measure radio intensity coming from astrophysics. Particular image was taken by VLA, which is a very large array, which is a kind of radio telescope, and it is taken at 90 centimeter wavelength. And what you are seeing are radio photons that are coming to us from the center of the galaxy. So there's a whole lot of things there. For example, I don't want to go into the details of everything and bore you with it, but whatever you are seeing as SNR, these are supernova remnants, which means they are stars which exploded long back. But of particular interest is this bright object over here. You can see it. It's marked as Sagittarius A star. Okay? Sagittarius is abbreviated as SGR here, Sagittarius A star. So astronomers back from 1970s itself, they have been monitoring this object, and it's a very persistent and bright object at radio wavelengths. So the current the consensus in the back, even 30 or 40 years back itself, was that the center of our galaxy, whatever is it, okay, whatever is present, which is so bright at radio wavelengths. So the center of the supermassive black hole. Now we know that it's a supermassive black hole, but the supermassive black hole is embedded within this region. So here's a picture of the galactic center taken by the Chandra X-ray Observatory. This is a telescope that is orbiting the Earth, and it is optimized to look at the universe at X-ray wavelengths. And the name Chandra comes from, the telescope was named in honor of Subramaniam Chandrasekhar. He's a very famous astrophysicist of Indian origin, who's also awarded Nobel Prize long back. So this false color image, this is again a false color image taken by Chandra X-ray satellites. It shows a region that is 400 light years by 900 light years across. Again centered on Sagittarius A star. So this is the Sagittarius A star region. You can see that it's very bright in X-ray wavelengths, and whatever is present in the center, okay, so we don't know what it is, that is the center of our galaxy. So these kind of multi-wavelength observations have been routinely going on for many years now in astronomy, and all of them show that the center of our galaxy is a very exciting, active region, but it's also a very crowded region. Now what Reinhard Genzel and Andrea Ghez and their teams did was to peer through the crowded region of gas and dust, look towards Sagittarius A star, pick out stars that are very close to the galactic center. So they picked out individual stars that are very close to the galactic center, and they monitored their movement, their dynamics, okay, how these stars are moving over long periods of time. And from that motion, they determine what could be the mass of the object at the galactic center. So how does motion help us to determine mass? Okay, the idea is very simple. Okay, so let's take the case of our own solar system. Okay, let's say that we cannot see the sun, or the sun is not emitting any light. Okay, but it is present in the center of our solar system. So the sun has mass, and it's present in the center of our solar system. And there are planets revolving around it, and we know that these planets are revolving around the sun because of the gravitational pull that the sun has on these planets. Now, even if the sun were not emitting any light, by carefully monitoring the orbits of these planets, we can actually infer the mass of the sun. That's because the planetary motions are governed by basic Newtonian laws of motion under gravity. Okay, so for example, I'm sure from your class 12 you would remember this equation. So this is a velocity of a uniform circular motion. If an object is revolving around an object of mass m at a distance r, then its velocity is going to be that. Okay, so if you measure the velocity and if you measure how far away the any planet is, then you can find out what is the mass enclosed within the orbit. Or the alternative is you can use Kepler's third law, which says that square of the period is proportional to cube of the orbital separation. So P, you can observe how long does any planet take to go once around the sun and how far away the planet is. From that, you can estimate what is the mass of the central object around which it's going. So based on the kinematics of objects that are going around a massive object, we can determine what is the mass of that massive object. And this is exactly the kind of things that the both teams, Reinhard Genzel and Andrea Gesse's team, looked. So they measured the positions and velocities of stars that are very close to the galactic center, and they used that to infer the mass that is present in the center of the galaxy. So the approach is follow the dynamics of stars close to the galactic center and use that to estimate the mass and size of the object in the galactic center. And as I mentioned, these observations were done not at visible wavelength regions, but primarily at infrared wavelength regions. So before I show you the actual results from their work, let me just tell you how these measurements are done. So measuring, well, how do astronomers measure velocities of stars in the galaxy? So let's say that you're an astronomer and you're looking at this star, and let's say that the star has a space velocity, a three-dimensional velocity in space relative to us, that's v. Now we can decompose that velocity into two orthogonal components. One component which is towards us or away from us, which we call as the radial velocity, and the other component is perpendicular to our line of sight, which is called the tangential velocity or the transverse velocity. So the actual velocity of the star will be the square of the sum of the squares and the square root of that. So quadrature sum of these two velocities. And so if you can measure the radial velocity and if you can measure the transverse velocities of stars, then we can measure what is its actual velocity. Okay. So the radial component of velocity will be perpendicular to the plane of the sky, which means it will be towards us or away from us. The transverse component of the velocity will be along the plane of the sky, resulting in a change in position of the star over long periods of time. So I will now show you how the radial component is measured and how the transverse component is measured. So the radial component is measured by recording the spectrum of stars. So the spectra of stars contain absorption lines, and these absorption lines are produced by atoms and ions present in the surface of stars. So what you're looking at over here is a small region corresponding to the spectrum of a star. Okay, the spectrum goes from very short wavelengths to very long wavelengths. So we are just looking zoomed into a small region. The red is the spectrum of a star that is close to the galactic center, and you can see some absorption lines. For example, here is a very prominent absorption line. This is also a prominent absorption line. This is also another prominent absorption line. These three absorption lines are coming to us from ionized calcium that is present in the surface of the star. How do we know it's ionized calcium? Because we know ionized calcium has absorption at certain wavelengths, so that can be used to find out that these are ionized calcium absorption lines, except for one problem, which is that when in laboratory, these are the wavelengths. Okay, so the x-axis is wavelength in nanometers, that's written here. These are the wavelengths in which we measure these lines. And we find that for this particular star that's very close to the galactic center, those lines are present, but they are not present where they are supposed to be, but they are a little bit offset. And the reason for that offset is the star is moving relative to us. So you may have studied Doppler effect. Okay, Doppler effect is there for sound. Doppler effect is also there for light. If a source that is emitting light is moving towards us, then the light will be shifted towards bluer wavelengths. And if the source is moving away from us, it will be shifted towards redder wavelengths. So here you can see that every line is offset from where it is supposed to be by a small amount of wavelength. This shift in wavelength can be used to compute what is the radial velocity. So this is how astronomers measured the radial component of stellar velocities. And the tangential velocity is measured as follows. Okay, so if you have a star present in a certain point in the sky, as the star moves with some velocity, its coordinates in the sky will change over a long period of time. It won't happen immediately, and that is because these stars are at enormously large distance from us. For example, if a star is at 1,000 light years from us, and if that star were to move 1 kilometer in 1 year, okay, in space, the angular displacement corresponding to that, delta theta here, it's going to be very, very small. Okay? So unless the star moves a lot in the sky, the angular displacement won't be much. So astronomers wait for many years and they carefully measure the positions of stars and see which stars are actually changing their positions, which helps them to measure the tangential velocities of those stars. And for the kind of stars that are present in the galactic center, the angular velocity, which is given as nu here, which is equal to angular displacement by the time taken for that displacement, is usually that angular velocity is of the order of milli-arc-second per year. Very, very small, okay, extremely small. And once you know what the angular velocity is, then we have this expression v is equal to r omega. I'm sure all of you have studied this. So that's the same here. The tangential velocity is how far away the star is and its angular velocity. That will give us tangential velocity. So we have radial velocity and we have tangential velocity. From that, we can determine what the velocity of the star is. So let me just tell you the difficulty in this measurement. Okay, so as I told you, for stars near the galactic center, since they are ridiculously far away from us, they are going to only move a tiny bit, even if you wait or keep on observing the star for several years. And usually the displacement, angular displacement, is the order of milli-arc-second. So in case you don't remember what milli-arc-second is, okay, so here is a protractor. Okay. Every line drawn in this protractor, every two adjacent lines, that is roughly 1 degree. So this is 30 degree, this is 31, 32, 33, etc. So you take any of those 1 degrees, you divide it into 3,600 bits, okay, pieces. Each one of those pieces is 1 arc-second. Now you again divide it into 1,000 pieces, that is milli-arc-second. Okay? So that is the kind of displacement that these stars exhibit over the course of a year or a few years. So it means that unless we can exactly measure the positions of stars, unless we take razor sharp images of the sky and the stars, we will not be able to measure these tiny movements. And without measuring those tiny movements, we can never infer what is present in the center of our galaxy. So this is an observational challenge. Okay? It's not easy, it cannot be easily done, and it cannot certainly be easily done with telescopes on Earth's surface. The reason is that Earth has this thick blanket of atmosphere. Okay? So the atmosphere is very important for us. It is what sustains life. But the problem is, this atmosphere is a nuisance for astronomers. And the reason for that is that the atmosphere is always turbulent. Okay? The atmosphere is constantly moving. It's in a state of flux all the time. So when a ray of light comes from space and enters Earth's atmosphere, what happens is that ray of light gets refracted as it passes through different layers of Earth's atmosphere. So every layer of atmosphere has a certain density, temperature, and chemical composition, which means that every layer of the atmosphere has a different index of refraction or refractive index. So as light passes through medium of different refractive index, it's going to bend, it's going to change its direction. So as a result, the image that the telescope can collect at the focal plane, at its focal plane, that image will be, quality will be degraded. So this is generally referred to as seeing in astronomy. So the turbulence of Earth's atmosphere degrades image quality. So just to give you an idea how bad the situation is, so here is a picture of a crowded stellar field. Okay, there are many, all the dots that you're looking at, these are all stars in our own galaxy in a small patch of the sky taken by an observatory in space. The advantage of putting an observatory in space is that you are above the Earth's atmosphere, so you no longer need to worry about the turbulence of the Earth's atmosphere affecting the quality of your image. So you can see that the stars are pretty well measured. Okay, every star looks like a point source. But if that same region, if you were to look with the telescope from ground, this is what you would see. The image is significantly blurred. Okay. All the tiny dots have now washed out because what you are looking at is a very blurred image. Okay? So it's something like, if you take a jump into a swimming pool, once you're underwater, if you look outside, everything outside will look blurred. That's because the turbulence of the water of the pool causes the light to blur out. Okay? It won't allow the light to focus exactly at one point over some period of time. So this is a big problem to get precise locations of stars. Now, there are space-based observatories, okay, from where you don't have this problem of atmosphere affecting your measurements, but space-based telescopes are only few in number. It's very difficult to get time at these space-based telescopes because a lot of astronomers are competing for observing time at these telescopes. So you have to do with ground-based observatories also. So as it turns out, interestingly, there is at least one way to compensate for this distortion of images due to the atmosphere, okay? And that is adaptive optics. So now we are coming into engineering and how engineering helps astronomy. Okay? Adaptive optics is a very cutting-edge technique where the optical system, which is connected to a control system, corrects for the blurring of images due to the turbulence of Earth's atmosphere in almost real time. It's very, very interesting. This idea was first proposed by an American scientist called Horace Babcock, okay, back in the 1950s. He put forth this theoretical idea, but the problem was that back in 1950s, the technology that was available in optics, etc., and electronics was not ready to deal with the kind of exacting requirements that were needed to successfully design an adaptive optics. So it remained a theoretical idea. In the 1960s and 70s, the US military started looking into it. So they put a lot of money to do research and develop adaptive optics system. Now, of course, their interest is not astronomy. The military was interested in coming up with better imaging systems that can do surveillance of Earth from satellites. Okay, so when you have a satellite at a certain altitude above the Earth's atmosphere, as the light that the satellite collects also gets affected by the Earth's atmosphere, turbulence in Earth's atmosphere. So adaptive optics was a technique that should help the military to get sharp images of various locations on Earth. So the military invested a lot of human resource and money into developing this adaptive optics technology in the 1960s and 70s. But because it was a military project, it was also classified. Only in the 1990s, the US military declassified it. And once the design principles, etc., became available, many fields, including astronomy, adopted this AO technology. AO is adaptive optics for short. Okay? And so since then, many observatories have this adaptive optics system to help correct images for the blurring caused by Earth's atmosphere. So I'll just quickly explain, since most of you are engineers, okay, so I'll just quickly explain the design of an adaptive optics system. So here is the basic schematic layout of how an adaptive optics system looks like. So the adaptive optics system goes as a back-end instrument to a telescope. Okay, so the telescope is not shown in this layout, but what is shown is the light coming from the telescope. That's this. And you can see that the wavefront, okay, so there are very many ways of looking at light. One is in the form of wavefronts, the other is like we draw ray diagrams. So you can look at the wavefront and you can see that the wavefront is distorted. Okay. Ideally, for a source which is at infinity, the wavefront should be plane parallel, like parallel lines. But here you can see that it is distorted, and this distortion happens because of the turbulence in Earth's atmosphere. So what the adaptive optics system does is, the two main components of it is, one is something called an adaptive mirror, which is also called deformable mirror. This deformable mirror is made of very thin sheet of glass with a diameter of a few inches, and attached to the back of this adaptive mirror are a set of actuator devices. Now, actuator devices are like hydraulic lifts which can push the mirror or pull the mirror in one direction or the other, different parts of this mirror. So the actuators are like these pistons moving up and down, and this actuator movement is controlled by a control system, okay? And that control system is fed information from something called a wavefront sensor. So what this wavefront sensor does is, it measures the distortion in the incoming light and it tells the control system what is the movement that it should initiate in the actuators, so that the mirror changes its shape in real time, so that the light that gets reflected off this mirror gets corrected for the distortion and becomes plane parallel once again. So this is happening in real time, which means that every millisecond the shape of the mirror keeps changing. Okay. So the control system would change the mirror shape in one way, and immediately within a fraction of a second the mirror shape is changed, because the wavefronts are coming, and each time the wavefront comes the distortion is going to be different. It's not going to be the same amount of distortion. So this is what the real-time correction looks like. And so this adaptive optics system is fitted in many of the modern big observatories. So I'll just show you one such example. So this is the very famous Keck telescope. The Keck telescope is situated on the summit of Mauna Kea in the island of Hawaii off the Pacific Ocean. Okay, so this is the telescope. This is the dome structure inside which the telescope is kept. And what happens is, for the adaptive optics system to properly sense the wavefront distortion, it needs a standard source in the same region of the sky where we are observing the astronomical object. So suppose I am observing the center of the galaxy, and the light is coming from the center of the galaxy, stars that are present in the center of the galaxy. Okay, so in order for the control system to sense, the wavefront sensor to sense what is the amount of distortion that's happening to the light, it needs a reference standard source in that same patch of the sky. Because you cannot go very far from that patch of the sky, because turbulence varies from region to region in the sky. So in that same patch of the sky that the telescope is observing, you need a reference star. Sometimes very bright stars are available as reference stars, but often the region of sky that we are looking at may not have any bright stars. So then what happens is, they create an artificial star in the sky by firing a high power laser up into the sky. And usually the laser that is used is a sodium laser. Okay, and the sodium laser goes up into the sky, and about 90 kilometers above the ground level, there is a layer of sodium that's present in Earth's atmosphere. So this laser goes and excites the sodium atoms in that layer, and those excited atoms, they fluoresce and they produce an artificial star in the sky, the same region that the telescope is looking at. So this artificial star is simultaneously monitored as the other stars in that field, and the wavefront sensor detects the amount of wavefront distortion by measuring the light from this artificial laser guide star. So this is called adaptive optics laser guide star system. Okay, and it's a very interesting technology. What I will show you next is a small video where whatever I just said, it has been confusing to you, maybe this video will help. It shows the entire adaptive optics in action. Okay, this is for the Gemini Observatory, which is an observatory of the European countries. Okay, so here is the dome structure, and there's the telescope. The telescope is moving and it's orienting and looking at a certain part of the sky. So a laser beam is fired like this, and it's a high power laser, so it reaches a very high altitude. It's a very coherent beam because it's a laser beam. And at about 90 kilometers, you have the sodium layer. The sodium atoms get excited. They start glowing. So when you look at this glowing region from ground, it looks like an artificial star. So this artificial star is used by the adaptive optics system to measure the extent of distortion that is happening to the wavefront. So light comes and falls on the telescope. It gets focused at the focal plane of the telescope where the camera, etc. is kept. This is where all the instruments are kept. So one of the backend instruments is the AO system, adaptive optics system. So this over here is the deformable mirror, and this is the control system. Okay. So when the control system is not active, the image of the star will be flickering a lot. It will be twinkling a lot, and so we'll be getting a very blurred image. The wavefront is distorted. That's what its incoming light is distorted because of Earth's turbulence, Earth's atmosphere's turbulence. Now, if the control system is switched on, then the actuators will deform the mirror thousands of times every second. And so in a direction that's opposite to the wavefront distortion, so that the light that is reflected off the mirror once again is plane parallel. And the image that is rendered becomes very sharp. So this adaptive optics technology was crucial for both teams to make the kind of discoveries that they did. Okay. So I'll just show you how powerful this adaptive optics technology is. So here is the planet Neptune without adaptive optics and with adaptive optics. You can see how sharp the image is. Okay. And so here is the center of our galaxy. So every object that you are seeing, like a patch of light, these are all stars. They should be point sources, but because of Earth's atmosphere's turbulence, they look like smeared objects. The light is blurred. Okay, but this is what happens when the adaptive optics is switched off. Now, if you switch on adaptive optics, then the image becomes very sharp. So once the image becomes very sharp, it becomes very easy to measure the exact positions of stars and carefully track their movement in the plane of the sky, and from that measure their positions over long periods of time. So on to the discovery. Okay, won't take much time, maximum maybe 5 or 10 minutes. So Reinhard Genzel's group, they used 2 telescopes for collecting their data. One is the New Technology Telescope, which is a 3.6 meter telescope in Chile. And the other is VLT. VLT stands for Very Large Telescope. Okay, it's a much bigger than NTT. And both these telescopes were used by Reinhard Genzel's group, and both have, NTT has something called active optics and VLT has adaptive optics, which we have been talking about. Andrea Gess's group were using these twin telescopes. These are called Keck telescopes, and they are at the summit of extinct volcanic mountain called Mauna Kea in Hawaii, which is in the Pacific Ocean. Okay, so they have been using these telescopes, which are also fitted with adaptive optics systems. Okay. So these are some of the largest ground-based observatories that are available to astronomers equipped with adaptive optics systems. And so these teams used these telescopes to get sharp images of stars in the galactic center, and as sharp as possible. So now I'll show you the results that led to the Nobel Prize. Okay. So these are first I'll show you results from Reinhard Genzel's European group. So this is an image that is 0.4 light years by 0.4 light years across. This image was taken by the VLT telescope by the European team headed by Reinhard Genzel. So what you're looking at, every black object that you're looking at here is a star that is very close to the center of our galaxy. If you pay close attention, you can see here Sagittarius A star written, and the arrow is pointing here, which means that the center of our galaxy, whatever is present in the center of a galaxy, that's here, okay, this point. Now all these are stars that are close to the galactic center. They are named S1, S2, S3, S4, etc., all the way up to S112, right here. Okay. So S means stars. Okay. So there are many stars, and without the help of adaptive optics, they would not have obtained this kind of a sharp image. So what the team did is they carefully measured the positions of these stars over a long time period, 20-25 year time period, and they found that these stars are not stationary, but they are moving very fast. And all of them are moving with respect to the location of Sagittarius A star over here. So all their orbits are kind of centered around Sagittarius A star. So this is from a 2009 paper that they published in 2009. From that same paper, they show the orbits of some of the stars which are very close to the center of the galaxy. So now earlier it was 0.4 by 0.4 light years across. Now we are zooming into 0.1 light year. Okay. So this is 0.1 light year distance roughly. And you can see that the stars are all orbiting around this point, okay, over here. So each one is a star. S2 is a star, S12 is a star, S29 is a star, and the orbits have different eccentricities, and the orbits have different orbital radiuses, semi-major axes. They're all elliptical orbits. Okay. So by carefully monitoring the velocities and the time periods, and by fitting Keplerian models to these orbits, the group was able to find out what is the mass of this object around which all these objects are going. And that, so it's basically Kepler's law, okay, but it's not as simple as shown in this expression. There are many layers of complexity to it, and based on those Keplerian models, they found out that all these stars are going around an object that has a mass that is roughly 4 million times the mass of Sun. So this symbol here represents mass of Sun. So this is 4 into 10 to the power of 6. That is 4 million times the mass of the Sun. They also found that that object, that center, is roughly about 8 kiloparsec away from us. Just to give you an idea, because of the adaptive optics system in the VLT telescope, they were able to measure the positions of these stars with an accuracy of about 300 micro arc second. Okay, so that's what it is. And the reason why these stars are called hypervelocity stars is because when these stars are moving very close to the center of the galaxy, they acquire speeds that are a few percentage of the speed of light. 1,000, 2,000, 3,000 kilometers per second. Okay? And that is because they are under the influence of a strong gravitational field of this massive object, okay, present here. And so that's why, because of those enormous speeds, they are called hypervelocity stars, these class of stars over here. Okay. Now, the same kind of result was also obtained by Andrea Ghez' group in the US. So here are results from their work. Okay. So what you are seeing over here are orbits of some of the stars which are close to the galactic center. Each dot corresponds to a measurement of the position of a star. So these are all measurements of positions of a particular star. Okay. If you look at this yellow thing, each one is a measurement of that star S02, and it's going around like this. And you can see that at some places there is no data. For example, if you take this orbit, these are all the points where there is data, and here you don't have any data, but they model it based on the available data. And based on that also, they were able to infer that the mass of the central object is roughly 4 million solar masses, and their accuracy was slightly better. And this kind of a mass is confined to a region that's roughly smaller than 100 astronomical units. Okay. So for example, these stars come as close as 100 astronomical unit to the center of that orbit. So 101 astronomical unit is the distance between Earth and Sun. So 100 astronomical unit means 100 times that distance. And so this entire mass is confined to a volume which has a radius of about 100 astronomical units, which is not very large. Okay, 100 astronomical units is not a large size. It's about the size of the solar system. So you think about it, okay? Million times the mass of Sun present in a region of space that has a volume of the solar system. The only object that fits that description is a black hole. Okay, so much mass confined to such a tiny volume, the object has to be a black hole. And then moreover, there is no direct radiation that one is getting from it. So whatever I showed you so far are static images, and here is an animation which shows the orbits of those stars. This star that is marked here, that is the center of our galaxy, and each one of the other object is a star which is close to the galactic center. And as I play the animation, you will see that the time of observation changes. It starts from 1995 and goes up to 2020. So 1995.5 means it's May 1995. So the month is given by here, the decimal value here. So up to 2020 April. Okay. So this is very important because this shows that it was not a 1 year or 1 month observation. These observations lasted for nearly 30 years, okay, 25 to 30 years. And only after that, they were able to properly map the orbits of these stars and determine the mass of the object in the center. So I'll just skip these slides. So now the question is, these groups have estimated the mass, but are these measurements showing us the supermassive black hole? Okay, are we actually looking at the supermassive black hole? Now, the obvious answer to that question is no, because by definition, a black hole itself is invisible. Okay, so there is no electromagnetic radiation that we can get from a black hole. So there is no question of actually seeing the black hole the way we see stars, planets, or galaxies. What is possible is to view the immediate surroundings of a black hole. So what do we mean by immediate environment? Okay, so the boundary of a black hole is often referred to as event horizon, or sometimes it's referred to as Schwarzschild radius. So this is the region surrounding a black hole singularity from where nothing can escape, not even light. So, and we know that in the physical universe, light is the fastest object. So if light cannot escape, then nothing can escape. No information can come to us. So that defines the boundary of a black hole. And general relativity tells us that if you have an object of mass m, then which is resting as a black hole, then the size of its event horizon or Schwarzschild radius is 2gm by c square, where c is the velocity of light in vacuum. So if you put the value of 4 million solar masses here, which is the mass of the supermassive black hole at the center of our galaxy, then we can find out what is the size of the event horizon of this of this black hole. In other words, what's the radius of this black hole, and the value comes out to be 12 million kilometers. So this may seem like a big number, but in the context of astronomy, that's not a big number. Okay, just to give you an idea, 12 million kilometers is less than the distance between Sun and the planet Mercury, which is the closest planet to the Sun. So this black hole's event horizon is very, very small, and this kind of a distance, this kind of a size object, if you keep it at a distance of 27,000 light years, which is how far away the center of the galaxy is from us, its angular size is going to be 10 micro arc second. And the kind of observations that they did with the VLT telescope and the Keck telescope does not have the angular resolution to see the event horizon or material which is very close to the event horizon of the supermassive black hole. So the observations which I showed you has not shown the region close to the event horizon of the black hole. Those results, those observations came from, I'm just skipping this slide since we don't have much time. Those observations came from another team of scientists, and they have not been awarded the Nobel Prize. So these observations came from with the help of something called the Event Horizon Telescope, which is a large configuration of radio telescopes scattered all over the globe. Okay, so this is not one radio telescope, but many radio telescopes that are simultaneously used to observe a patch of sky, and they will mimic the kind of observation that a telescope as big as Earth would see. That's called very long baseline interferometry. It's a very advanced technique, and using that, astronomers looked at the center of the galaxy, and so they saw this glowing disk of material at radio wavelengths. Okay, so this is a glowing circle, and I'll tell you what it is. Okay, so what we are looking at is the regions very close to the supermassive black hole. You can see the size here. It says roughly 200 micro arc second. So the size of the event horizon was 10 micro arc second. So we are looking at roughly a region that's about 20 times the size of the supermassive black hole. So the supermassive black hole is somewhere in the center of this, but the kind of observations that is possible with Event Horizon Telescope cannot resolve the event horizon of the supermassive black hole. You can only see material within it. And the reason why the material close to it is so bright is because the black hole is taking that matter in, and as this matter spirals into the black hole, because of viscous frictional forces, it gets heated. And once it gets heated, it starts emitting radiation. Okay, So that radiation is what is detecting. And so currently, as of date, this is the closest that astronomers have gone to observing the supermassive black hole in the center of our galaxy. Okay, so what you're looking at here is the closest that astronomers have gone in imaging the supermassive black hole in the center of our galaxy. Okay, so there are a lot of unanswered questions. For example, in astronomy, we don't know how these supermassive black holes with masses of 1 million to 1 billion solar mass, how do they form in the centers of galaxies? What is the source of these supermassive black holes? Where do they come from? And also, it is not very well known what role does a supermassive black hole play in the formation of a galaxy and in its subsequent evolution. So these are unanswered questions, but there are many interesting research work that is happening in this direction. So just to sum up, I'll just say that black holes are perhaps one of the most mysterious among objects in nature. Black holes can warp because of their tremendous gravitational field. They can warp space and time in extreme ways, and more importantly, black holes contain a mathematical impossibility, which is a singularity. Singularity means that you have a large amount of mass confined to zero volume, okay, which means infinite density. Infinity is not something that theoretical physicists like, because it messes up your equation. So that's what I meant by saying that there's a mathematical impossibility associated with black holes, which is its singularity. The work of Andrea Ghez and Reinhard Genzel and their team of students and postdocs is one of the most convincing evidences currently available to us on the existence of supermassive black holes in the center of our galaxy and also in the center of other galaxies. It's a great example of how technology and careful observations, and of course a lot of patience, can come together to unlock the secrets of the universe, and probably also shed a lot of light on what is possibly the darkest of objects in the universe, which are these black holes. So there's a lot of work happening in this field, and in the coming years, I think many more interesting discoveries are likely to come. So with that, I'll just stop my presentation and I'll be happy to take questions that you may have.
Thank you, sir. Thank you so much. From the audience, if anyone is having any questions, you may unmute yourself and ask.
So I think I went at a lightning speed, okay, because I had a lot of slides. So I don't know how much of it was at a pace that you can follow, but you feel free to ask questions. So Aparna is asking in the chat window, are there plans for India to start the LIGO? Okay, so LIGO refers to gravitational wave observatory based on laser interferometry. It's a global collaboration between many countries, and India is also part of LIGO. Okay, the Indian version of LIGO is called Indigo. Okay, Indian LIGO. That's what it is, and India is already part of the Laser Interferometry Gravitational Wave Observatory. So in fact, India is actually, Indian government is actually heavily investing in fundamental research in science and technology. So there are many prestigious global astronomy projects that India is now a partner in. Anything else?
Hello, sir. My name is Jitin, and
yeah, Jitin.
I have a doubt about that singularity. As you have said, the black hole converts all into that singularity, and by Big Bang, we mean that our universe was formed out of a singularity. So my question is that, so is there a possibility that there was something before that singularity, before Big Bang happened? Is there something like a black hole to form that singularity?
Okay, so that's a great question, Jitin. So firstly, let me say that the primordial seed of our universe, from which the entire universe came into existence, I don't think people think of that as a singularity, but you're right that the description is Correct. Okay, a lot of something confined to zero volume, but people don't talk about it in terms of singularity. Okay, and the other thing is what was there before the birth of the universe. So for people who are not aware of this, the current consensus in astrophysics is that there is an overwhelming amount of data that suggests that our universe had an origin roughly 13.7 billion years ago. A billion is 1 followed by 9 zeros. So roughly 13 billion years ago, our universe had an origin. This is called the Big Bang. So Jitin's question was, what was there before the Big Bang? Okay, so now my answer may seem like a way to escape your question, but this is actually the answer that is put out. See, Big Bang was the origin of our universe, which means that everything that we see in our universe, matter, space, and time, okay, everything came after the birth of the universe. So all the things that we see around us came after the birth of the universe, including space and time also. Which means Big Bang was t equal to 0, time is equal to 0. Okay, so time itself came into existence at the moment of creation, and therefore there is no before that. We cannot ask what was before Big Bang because, we can very well ask, but within the framework of physics, we cannot answer it because physics makes use of space and time as its framework to mount its theoretical ideas. Okay, so that is the framework in which all the theoretical ideas in physics are mounted, space and time. And the problem with it is that time itself came into existence after the universe created, or at the moment of creation. So with the known laws of physics, we cannot address what was before because there was no before. Okay, so an analogy is, let's say that you are standing at the North Pole of Earth, and somebody were to ask you, can you point me to the North Pole? Okay. Every direction that you point will be pointing towards south because you are standing at the North Pole. Similarly, the arrow of time started from the moment of creation, so there was no before for it. Okay. So, yeah, that's my answer to the question. I don't know whether it makes sense. Okay, so there are a couple of questions which have come in the chat window. Anandu has asked, do you believe in the existence of parallel universes? So Anandu, what do you think? You can unmute yourself and...
Not sure, sir. There are theories all around the internet.
Yeah, so see this, observationally, there is no evidence for the existence of parallel universes, but I'll tell you where it comes from, okay? So once you go into the subatomic world, once you go into the microscopic world, okay, one of the fundamental ideas of quantum mechanics, which is the physical law or physical framework that describes the microscopic world. So according to quantum mechanics, at the microscopic level, at the subatomic level, the universe is not deterministic. It is probabilistic. What I mean by that is, even if you know everything about the universe at the microscopic level, you can never predict with absolute certainty that an event is going to happen. Okay? You can only say that an event can happen with this much probability. So from a deterministic worldview, so the world that we live in is a deterministic worldview. Okay? But at the subatomic realm, we enter into the probabilistic worldview, and this probabilistic worldview is not because of our limitation of understanding the microscopic world. What quantum mechanics is saying is that, quantum physics is saying is that it is an inherent property of nature that it is not deterministic, it's probabilistic. Nature behaves with some uncertainty always. So now what this means, so this is the seed of this idea of parallel universe, which means that at every point, a certain event in a microscopic world has a certain likelihood of happening this way and a certain other likelihood of happening that way. So then what it means is that at that point, the universe splits into two. In one of the universes, the event happens, and in the other universe, the event doesn't happen. Both universes exist. Only when an observer observes the system does one of the universe collapse and the other one comes into manifestation. Okay. So this is, if you are finding it really bizarre, then let me tell you that even some of the best minds find it very difficult. Okay, so Einstein famously remarked that God does not play dice with the universe. When he first encountered this probabilistic nature of at the subatomic realm, this is what he said. What he meant by that is he found it very difficult to digest that the universe cannot be deterministic. Okay, the universe can have this inherent uncertainty. So it's very difficult, but this is the sum and substance of quantum physics. And so the idea of parallel universes come from that. Okay. So if you are interested, I would encourage you to go and read about Schrodinger's cat. Okay, maybe some of you have read about it. You can go and read about Schrodinger's cat. Yeah, so this is a theory. This is the thought experiment where they tried to show how parallel universes can come, with an experiment where you have a cat, a bottle with some poison in it, and a radioactive material, all kept inside a box. Okay, so it's a very interesting thing. You can go and read about it. Is there any relation between, Gauri is asking, is there any relation between gravitational waves and center of our galaxy? Is there any evidence for the existence of gravitational waves? Okay, so the second part of the question I will answer first. Is there any evidence for the existence of gravitational waves? Yes. 2019 April, the gravitational waves were detected now several years ago, and currently now there are more than a dozen instances where gravitational waves have been detected in the universe coming from different astrophysical systems. And so gravitational waves are essentially, they are not electromagnetic radiation, they are ripples in space-time. Okay, so they are ripples that are created in the fabric of space itself. So that is space itself undergoing compressions and rarefactions. That's what gravitational waves are, and they have been detected from different parts of the universe using detectors like LIGO. Okay. And the first question was, is there any relation between gravitational waves and the center of our galaxy? Okay, so people have been trying to point gravitational wave observatories to the center of our galaxy, but as I understand it, okay, I'm not perfectly familiar with this work, but as I understand it, the current frequencies in which gravitational wave detectors operate are not suitable for detecting gravitational waves from the center of our galaxy. So some refinements have to happen in the gravitational wave observatories for it to be able to detect ripples from the center of our galaxy. Okay, so sir, I have heard that as we move close to a black hole, time slows down, and at even horizon, time stops. It just blows my mind. Can you explain? Okay, that's a very tough one to answer, Savitri. Yeah, so the time slows down not for the person who is going into the black hole, but for a person who is standing far away from the black hole and looking at a watch that the person who is going into the black hole is wearing. Okay, so in other words, for a person in a different frame of reference, the time seems to be slowing down for somebody who's going into it. Now, this is because of special theory of relativity, which says that our measurement of time and our measurement of distances are all relative to each other. Okay, so I don't know how else to explain it in words. So I think that, but there is plenty of online material where you can actually see this concept being explained with the help of some very useful animations. Okay, so yeah, I'm just taking questions from random. Sir, can you explain about the picture of M87 black hole and extra dimensional possibility? I think Sahana has also asked the same question. Is there any chance that black holes could be wormholes in disguise? Okay, so this M87 black hole was very famous last year. Okay, so if you have been following astronomy news regularly, you would have seen that back in April 2019, there was a press release that a team of astronomers using the Event Horizon Telescope have taken an image of the region surrounding the supermassive black hole in the center of the galaxy M87. So M87 is a galaxy that's roughly about 16 million parsec away from us in the center of a galaxy cluster called Virgo cluster. And this supermassive black hole in the center of this M87 galaxy was 1 billion times the mass of the sun. So it's much bigger and more massive than the, not much bigger, but it's more massive than the black hole in the center of our galaxy. So that picture, you must have seen it. It shows a glowing region and a hole in the center. That hole. So what you are looking at is the periphery of that black hole in the center is the event horizon. And the glow surrounding it is from material that's present in the immediate vicinity of that black hole, which is glowing because of frictional forces within it heating it up. Okay, so that's what it is. Extra dimensional possibility, I don't know whether there are any other dimensions beyond the 3 spatial dimensions and time. There is a branch of physics called string theory where they often talk about additional spatial dimensions. There are some string theory equations which invoke 10, 11, 12 dimensions. But as far as I know, there is no real observational evidence for these extra dimensions. They are used in theoretical context, but observationally not found, I think. So Sushmita is asking, can you briefly tell about dark matter and dark energy? Okay, so dark matter and dark energy are the 2 mysterious components of the universe, which astronomers have no idea what it is, except that they exist. Okay, so all the things that we see around us, including ourselves, we are all made of what is known as baryonic matter. The baryonic matter is a collective name for matter which is made of protons, neutrons. Okay, and so everything around us, including ourselves, we are made of this baryonic matter. And observations in the last 20 years or so, and even more than that, has shown that this baryonic matter is only a tiny fraction of the total energy budget of our universe, energy density of our universe. The baryonic matter, that is what stars, galaxies, interstellar gas, dust, planets, black holes, neutron stars, white dwarfs, all these things are made of ordinary baryonic matter. This baryonic matter accounts for only 4% of the energy density of the universe. 96% of the energy density of the universe is in a form that we cannot directly observe. Among this 96%, about 25% or 20 to 25% is in a form that interacts gravitationally with baryonic matter, and it's called dark matter. The reason why it's called dark matter is because it doesn't emit any electromagnetic radiation, including light that we can see. Therefore, it is dark. But they are not black holes. Okay, black holes are made of baryonic matter, ordinary proton, neutrons, etc. Whereas dark matter is non-baryonic matter. Nobody knows what it is. So in the field of particle physics, there is a lot of interest because there is a potential discovery to be made on what the composition of dark matter is. Dark energy is the remaining 75%, 70 to 75% of the universe. And dark energy, no one has any idea what it is. Dark energy seems to be the reason why the expansion of our universe is accelerating, is increasing. So some of you may know that we are living in an expanding universe. What that means is the distant galaxies are all moving away from us. And the rate at which those galaxies are moving away from us, that rate seems to be increasing. And that increasing, so that is when a velocity increases, that's called acceleration. So the rate of expansion of the universe increasing is acceleration of the universe, and this acceleration is thought to be caused because of dark energy, which constitutes about 70% of the universe. But beyond that, astronomers have no idea what dark matter is or dark energy is. There are some hypotheses on what dark matter could be, what dark energy could be. Hypothesis is not a theory. Hypothesis means educated guess. That's all it is. So there is a lot of discovery that is going to happen in the next 30, 40 years because 96% of the universe is made of something that we have no clue what it is. Okay, so some of the questions that are being posed, I have no idea how to answer them because I don't know anything about it. So Gauri is, for example, asking, will this invention of the center of galaxy lead to the origin of the universe? So I don't know, Gauri, what you mean by that. Okay, the origin of the universe is something very different from the center of our galaxy. Our galaxy is only one galaxy in a universe with billions of galaxies. So there is our galaxy is like a dust in the entire cosmos, okay, the entire universe. So the center of the galaxy means nothing to the universe. It means something for us because we are part of this galaxy, but beyond that, at the scale of the universe, the center of the galaxy is nothing of no consequence. So I don't think the center of our galaxy and the presence of a supermassive black hole in the center has got anything to do with the origin of the universe. Your other question is this invention the beginning of any other greater inventions, or where will this invention lead to us? So I think what you mean by the invention is the realization that there is a supermassive black hole in the center of our galaxy. So that, as I said, the story is not complete yet. Okay? The astronomers have found out that there's a supermassive black hole, but there's a lot of questions related to it. What processes lead to the creation of black holes with 1 million solar mass? Okay, how do these black holes form? Astronomers know how smaller black holes form. Smaller black holes form when massive stars die. Okay, when massive stars stop, when massive stars explode as supernova, what remains are either a neutron star or a black hole. But these are much smaller mass black holes. Supermassive black holes, nobody has any idea how they form. So that's probably an area where there's going to be some important discoveries happening. And also the activity in the center, because of the presence of a supermassive black hole, what is happening to the material surrounding it? Okay, so this is a very interesting investigation problem because it involves general relativity. It's a test of general relativity. So that's another area where work is going to happen. KB Srihari is asking, sir, are tachyon particles really there? Is there any possible way we can harness them? So Srihari, to the best of my knowledge, tachyons have not been observed. Okay, faster than light particles, they have not been observed. So I don't know whether there is any way to harness them because they have not been detected. Okay, so I think that's probably, I know that there are many more questions, but some of them I don't have any idea. So maybe we can wrap it up. Gayatri.
Yes, sir. Sure, sir. I think there are many people more coming up with questions. Anyway, we'll wind up the session. Thank you so much, sir, for being with us, spending so much time and making such good presentations and actually creating a sense of excitement within us. Also, I'm sure many of us would actually go out in the night to spot the Sagittarius star today, maybe, because that's the curiosity which you've generated among us. Thank you so much for spending such valuable time with us. Thank you, sir.
Thank you. Thanks a lot. I hope to see all of you in the post-COVID era when I visit TKM maybe sometime next year. Thank you. Thanks for joining in.